Greetings, my name is Nokuthula, and today I have the privilege to give you an overview of my master's project thus far on the topic of adsorption of lead from aqueous solutions utilizing an untreated mining influenced water or MIW sludge as a low-cost adsorbent or LCA. This project is under the supervision of Prof. Brink at the University of Pretoria in the Water Utilization and Environmental Engineering Division in South Africa. The mining influenced water sludge is a waste byproduct generated during the treatment of mining water to potable water in Emalahleni in Mpumalanga, South Africa. I will briefly cover some theory on the contaminant, its dangers, and treatment technologies. I will also cover the adsorption studies conducted as well as the material characterization. The use of lead across various industries has shown an overall increase over the years, exponentially so in the manufacture of lead-acid batteries. Lead finds its way into the environment through various anthropogenic activities. Human exposure occurs by ingestion of contaminated food or water, or by the inhalation of dust particles. Prolonged exposure can cause health issues, particularly to children's cognitive and behavioral development. The EPA lists lead as a priority pollutant due to its widespread use, bioaccumulation, persistence, and toxicity. Various conventional techniques are used for lead remediation. These include chemical precipitation, ion exchange, membrane filtration, and electrochemical treatment. These methods have drawbacks, which range from their high operating costs to high chemical demand. Adsorption is regarded as a desirable option as it is an effective, simple, and robust method. However, the cost of conventional solids, such as activated carbon in the form of PAC and GAC or GAG, has a prohibitive effect on the use of this technology. This is because the material tends to be relatively expensive and proves to be challenging to regenerate. As a result, the use of LCAs is crucial. This study aims to ascertain the feasibility of using mining influenced sludge for lead adsorption, thereby aligning with waste valorization principles. Batch studies were conducted to obtain optimal operational parameters, allowing for future predictive modeling as well as upscaling. From the batch studies conducted, the material showed little sensitivity to pH in the range studied. The ambient pH of the solution was therefore selected. Optimal conditions for a removal efficiency of above 98% were an initial lead concentration of 300 mg per liter, a dosage of 1 gram of adsorbent per liter of aqueous solution treated, and a contact time of 90 to 180 minutes. Particle sizes of approximately 1, 2, and 3 millimeters were used for modeling with the aim of upscaling in future studies. Kinetics were modeled by pseudo-first order and pseudo-second order kinetics. The latter provided the best fit for the generated data. Freundlich and Langmuir isotherms were also fitted to isothermal data obtained at 25, 35, and 45 degrees Celsius. It was found that little variation occurs in the material's performance as material changes. One isotherm is therefore fed to the data, with Langmuir providing a better fit and a maximum adsorption capacity of 684 milligrams per gram. Low-cost adsorbents can be grouped into 5 groups depending on where they are sourced from, namely natural materials, industrial byproducts, agricultural waste, forest waste, as well as biotechnology-based low-cost adsorbents. Here, maximum adsorption capacities of adsorbents from each category are noted. When compared to other industrial byproduct-based LCAs investigated for lead adsorption, the material performs quite well, especially when considering its simplicity in that it is simply dried and milled. The material's crystalline structure is shown on the XRD diffractogram. The main components of the MIW sludge is gypsum. Small amounts of magnesium, iron, and silicon are also present due to the overall composition. Relatively high calcium, sulfur, and oxygen weight percentages are seen in the indicated EDS spectrum. This can be supported by the XRD showing high percent composition amount of gypsum. The presence of magnesium, iron, aluminium, and silicon is likely due to the occurrence of brucite and tremolite in the material. The presence of lead in the spectrum post-adsorption confirms the fate of the lead in the aqueous solution. The XPS further serves to prove that the lead was indeed adsorbed onto the MIW sludge. FTIR before and after adsorption shows no sizable difference in the peaks, which suggests that the material is quite stable. This is also seen on the same images. MIW sludge is a non-uniform heterogeneous material with irregular particles. It is also fairly porous. Little difference is seen in the total surface area of the material at different particle sizes of less than 75 micrometers to 3 millimeters. This again alludes to the porosity of the material. The result is positive as it suggests that the use of particle sizes similar to those seen in GAG does not negatively affect the material's performance, thereby allowing us to explore the avenue of upscaling in your packed bed type experiments where back pressure would have otherwise proven to be a challenge. MIW sludge is shown to be a feasible low-cost adsorbent for lead adsorption. The summary of results shows optimal performance at the ambient pH of the solution at 5, initial lead concentration of 300 milligrams per liter, a dosage of 1 gram per liter, a contact time of 90 to 180 minutes, the difference being due to internal mass transfer effects, and an ambient temperature. Pseudo-second order kinetic model provided the best fit at an R-squared of more than 95%. The Langmuir isotherm also provided the best fit at a Qmax of 684 milligrams per gram. Priority is to look at post-adsorption management, i.e. regeneration, reuse, recycling, and lastly safe disposal. The modeled kinetics might be able to then predict the breakthrough curves in continuous flow processes. The next step will be designing a column to test the performance of the material in continuous flow process as well as to show the accuracy of the models. Thank you very much for your time.